now we're talking about implementing systems engineering at the Brazilian Synchrotron. It's a presentation for our workflow for enhanced beamline design. I'm talking on behalf of the Maré Group, which is in the beamline engineering division from the Sirius Synchrotron. First of all, this presentation is divided on 3 parts. My first part will be telling you who we are, what do we do. Then Cassiano will take over, talking about Capella-based systems engineering, our starting workflow. And Débora will finish up saying which softwares are we integrating with Capella right now. So for a little bit of context, what is a synchrotron laboratory? It's in essence a giant and powerful microscope composed by 3 particle accelerators, 1 linear, which is this one indicated on the screen, and 2 circular. The first one is the booster. The second one is the storage ring, right? The main accelerator. And they are responsible for producing lights to the beamlines, which in turn use this light to investigate all kinds of materials in resolutions that can reach the size of an atom, as you can see by the diagram from the broad spectrum of light that is produced here. So Sirius currently is not the only synchrotron in the world, not even the only 4th generation synchrotron in the world. There are many machines like this in the world, but lately all the machines, they started upgrading from the so-called 4th generation, which is essentially new arrangements for the magnets that grants better light properties through better electron focalization on the accelerators and better trajectory stability, which in turns give you orders of magnitude gain in comparison to the previous generation. So today, this is one of the 3 4th generations in operations today. So today we have APS and Max 4 and ESRF sharing the space with Sirius, actually 4 now. APS just opened, and we have other 2 in upgrade construction phase, right? So essentially the mission for a machine like this is to understand and unravel the structure of diverse materials. When we do that, we may understand diverse mechanisms and processes related to these materials. And with this, we can validate and create new technologies. To do this, we make use of new experimental techniques that are always being thought out by the scientists here. And to viabilize that, we have to employ new technologies. And this closes the virtual cycle where we use this machine to create and ultimately create and validate new technologies. And we can apply these technologies to perfect even more the machines and enhance our capability of seeing, uncovering new things, right? So at this point, I think it's clear that we are not the Obeo Eclipse 2. We are a particle accelerator instead. And we are, in fact, the 2nd synchrotron laboratory in Brazil. We replaced the first one, UVX, that operated for 30 years in the same site. And we are now one of the brightest light sources in the world, having only 3 other comparable at the moment. But they are all in the Northern Hemisphere in developed countries. We are a research facility open to users worldwide. And to give you a little bit more of context, we are in a campus, in a scientific campus, inside the Brazil's National Center for Research in Energy and Materials. This research center, it hosts 4 national labs. One of them is Sirius. the NLS. The other 3 ones are LNBR, that researches biorenewables, LNBio, that researches biosciences, LN Nano for nanotechnology, and we are now building a 5th one that is meant to do research in pathogens to respond for better for pandemics like COVID. And it will be a maximum biosafety lab that it's attached to the synchrotron light source. So in this sense, we are working for both these labs, LLS and Orion. All 3 of us that are presenting now, we are part of the Beamline engineering division called DEL from this group called Mare. And the group, among many tasks, has the task of delivering complex experimental systems to Sirius and Orion with a high degree of assertiveness. And the idea is to tackle this complexity by implementing formal systems engineering with other groups of the lab. It's not a sole mission. Actually, we have almost 400 people working on the lab among the 3 scientific divisions and the 4 engineering divisions. So for a beamline to become a reality, all of these people are working. And Mare, it's not the only one on the beamline engineering. We actually work with all the other groups to build and maintain beamlines throughout their full life cycle, right? So in essence, for the beamline design to take place, the scientific groups, they work together to create experiments that meet industry and scientific community needs. The engineering groups then work together to create these instruments that meets the experimental needs. And every one of the beamlines that are here, they are custom built to address a specific group of techniques designed to extract specific information from all the analyzed material. So in the same building, the same lab, there might be dozens of beamlines all working simultaneously, analyzing different samples, or even the same sample can walk from one beamline to the other. So now to have an idea of how we are today, as you can see, the building from inside looks like this. We have the accelerator inside this protection, this radiation protection, and the beamlines fanning out from it. As you can see, there's plenty of room for our next beamlines. And if you see on the plant design, for the phase 1 from Sirius, we built 15 beamlines with about 4 beamlines per year, 3 to 4 beamlines per year. And in the phase 2, we want to build 13 new beamlines in the next 4 years, with a difference that we are also building this BSL-4 laboratory that will host 3 beamlines and will be the first in the world, with the idea of being able to respond quicker to pandemics by understanding the full cycle of diseases and understanding the structure of viruses and the full cycle of the infection, right? So now to go over what really is a beamline, right? It's essentially, to make an analogy, each beamline is seen as a system of systems working together to bring an experiment to life. So one may see a beamline as an airplane, as complex as an airplane, right? So you have, for starters, all starts with the source, which is here. It's the first component that actually is attached to the third accelerator, the storage ring. It produces the light, and this light is then conditioned by many systems, like the mirrors that were actually, was in the first slide. So they can focalize or reflect the mirrors to where to the beam to where they have to be. Monochromators also, they condition the properties of the beam. to select, for instance, a certain wavelength that will be used to interact specifically with the samples that are then in the experimental station. And once the beam is with defined properties, it will be used at the experimental station to interact in a specific way with the sample and to deliver specific informations to the detector. So the experimental stations themselves, they are complex systems by definitions too. They might have nanofocusing optics. They might have sample manipulation systems and sample environment systems. And of course, they have many detectors around the sample. Like this example of Taruma station, that is a multi-technique experimental station with nano resolution. And it's used to study many materials in many perspectives, like soils, biological samples, rocks, everything that has to be seen with a high resolution. And even in ambiental conditions, like in this case, there's a cryogenic setup where we actually we submit the sample into an environment of 122 Kelvin, and it has to be very, very dry. So in this case, we have to blow the sample with cold nitrogen and then pull all the air back to prevent the rest of the station to be exposed to low temperature. So it's an example of competing needs that we addressed later, and everything works fine. If you see in the video that passed here, actually we managed to keep the thermal drift within 1 micron for 7.5 hours. So this is obviously a result of a systemic approach, right? So for another example, Smogno Beamline, which is being designed to investigate porous media flow in rocks from the Brazilian pre-salt reservoir, and in a zoom tomography fashion, right? So this beamline can also generate data from other kinds of samples, like soil, as you can see from this video here. And for instance, investigate the interactions between roots and soil in 3D, right? So now we understand here that beamlines are complex systems. They are highly connected. The modules there are highly connected. The performance is highly sensitive to more than one module. And they often present competing requirements. For instance, temporal resolution versus spatial resolution versus environment conditions to meet all of them in the best case. At the same time, we probably need to balance all the requirements, right? So in that case, for one beamline to become reality, many different stakeholders are often involved, speaking different languages, different points of view, having different restrictions or needs. And since the science evolves with time, in beamlines are designed to be there for many, many years. Within the beamline life cycle, we often have upgrades to keep up with scientific community demands. So we need to have reusability. We need to have to consider technological heritage, and these are opportunities that we have in the many beamlines that are yet to build on this synchrotron. Only for this synchrotron only, we have 25 beamlines, for instance. So for my last slide here before Cassiano, I just wanted to say that we had the first institutional application of thermal systems engineer in even embryonic model-based systems engineer last year. So we are starting to develop this case. Of course, we understand that with the better capabilities offered by fourth generation synchrotrons, we have to push for technological advancement. So it's a great opportunity to start applying systems engineering. We are looking for collaborations. We are starting these collaborations inside and outside Brazil. And our main goal is to start showing value in improving future projects with quick and easy application of systems engineering in MBSE concepts. So we're not bound to any specific tool, although Capella is helping us a lot on that. And it's as you will see, we are applying, trying to show value as fast as possible.
So hello everyone. It's a pleasure to be here to talk to you today. I would like to thank you, Obeo, for inviting us to be here today and to be possible to show this presentation for you guys. And I would like to do a disclaimer here that the work that we are presenting here today is not the work from our three here that are here, but the work of a small team here in CNPEM, inside Maré's team, but outside also, and with a huge help from Adrian Unger also. I hope that he's in the audience. So I'm going to show you for you now a little bit of the workflow that we are designing and trying to apply for Sirius. So according to COSI, the projects, when we develop a project, we should, or it's advised to us to go on a lot of different steps, generally represented by the V diagram. As Moreno said to you guys, laboratory here, we have people with 30-year experience and a lot of people with more than 10 years experience. So in fact, we never applied all the steps of the V diagram, but in a kind of sense, by the experience of everyone knows what should be done at each point of the project. But as Moreno also said, Sirius is growing, so we are growing fast. We passed from 100 of employees some years ago to almost like 1,000 employees today in the whole CNPEM. So we need a different kind of structure, a different kind of process to deal with this more complex system, more people, more experience involved, more new people getting in the laboratory. And this is why these are most motivation to try to apply the system engineering tools and the system engineering methods here at CNPEM. So our presentation here today, the workflow that I'm going to present is going to be focused in this first part of the V. That's most part of what we are doing now for Orion projects or for Magno project also. But we are also overseeing already, that's not covered in this presentation, but the link between the two legs of our V diagram to develop a full process integrated with all other things in LNLS. So we are not, in fact, following the Arcadia method by the book, but our workflow is heavily biased by the Arcadia method because it was one of our first scratches on the surface of system engineering. So what we propose here, what we are trying to do, as Moreno says, is to show a easy and quick value so we can buy more time to work in it. And what I'm going to show, it's more or less this workflow that's in the screen. We're divided in two different blocks that's represented by the dashed line at the middle of the line. So the first block is more what we call the solution domain. So where we are trying to understand the problems, understand the stakeholders, understand what the stakeholders want for our systems, and understand what they expect our systems to do. And at the bottom, the bottom set, we are more at the solution domain. So we are trying to propose solutions for each one of the functions or each one of the capabilities that were defined in the first scenarios, and see and prove why these are the best solutions to go on in our model. So I'm going to pass quickly in each one of the steps to tell a little bit more of what we are thinking then. So as our first step, we are trying to identify the system interfaces and capabilities. So in a very top level, try to identify all the other systems that will be around our system, the beamline. So not always we are building a beamline from scratch. Sometimes we are upgrading beamlines, or sometimes we are upgrading end stations, or building a new end station for a beamline that already exists. So it's very important for us in this part of the project understand what are the other systems that are already built or are being built for the beamline, and which are the people that will use the system at some point. So we can't know all the users around the world, but we can know the beamline staff here inside CNPEM and the other groups around the beamline staff also. After understand this interface of our systems, we start with the requirements. So applying requirements engineering. So we talk with a lot of people, a lot of stakeholders, scientists, engineering, physicists, management, industry also here in Brazil or outside Brazil. So a lot of different meetings, a lot of different requirements coming from all the sides, a lot of different needs coming from all the sides. And we try to do a quick and dirty list of all these requirements, all these needs that came to us. And most important, we try to attach to these needs and requirements the rationale behind them, because we don't want to know just what you want, but you want to know what you want and why you want that. So we can, and when we go on the project with them, we can refine them and set them in the other requirements. So after we do this step of raw requirements and getting the needs of the stakeholders, we move to the refined requirements. So for each requirements, we try to break it in more requirements that are more refined, and not yet in the component level, the part level, but more in a high engineering level. And after we do these refinements, we try to input it in a more visual way to understand all the requirements relate to each others, and all the requirements are competing with each others. So we understand more the problem, understand more what the stakeholders want for the problem. After that, we try to understand how we can deal with the problem. So understand what's the flux of information, of mass or energy that it's expected to go around the problem. So we can receive samples, it can be inside our system to build the samples or things like this. So what is expected from our system, what we already have in the systems around our system, what we want the actors to have, or the interactions between human and machine. And so we can filter the functions from our system and do, and at this point we try to do also a lot of abstractions. Scientists are very creativity, so they are always trying to do solving the problem with also a solution. So we try to keep things neutral at this part, but then we move to the next part, that's the solution domain. So we try to analyze all the solutions in our system, try to start to propose solutions for it. Then here we try to employ the most creativity that we want. We are generally working with first of the kind systems as Orion laboratory. So not every time we can see around what we can do, what we can't do. Sometimes we have to try or model it to do. And at this point, we are trying to figure out the solutions for each one of the functions and try to use the 30-year experience that we already have inside here, the Sirius laboratory. So after identify the solutions, we need to identify which is the best solution. So at this point, we start some trade-offs analysis, looking for performance, costs, schedule also, using low fidelity models, because we are at the very start of the project. We're not trying to spend a lot of time in doing very specific models for this one. We are just trying to see around the solutions that you propose at the last phase, how we can deal with it, and which are the most promising solutions. And after we have the most promising or the most promising solutions, we can move to modularization. So as Moreno showed also, LNLS is a huge team. So we have a lot of different groups and different teams inside the laboratory that has much more experience than Mare's group and other kind of systems, so electronics, control, mechanics, mechatronics. So we try to modularize the systems, look at the organizational structure of CNPEM, so you can change, or so you can deliver different models for different things, and these models should be aligned with their specialities around the different things. And how we do this is trying to document all the workflow or all the information that gathered in this first approach of the projects, and then distribute it to a lot of the different things at CNPEM. So in the workflow, it seems to work very fine, but when we try to do it in real life, it's a little bit different. So Débora is going to show you how we are dealing with softwares and the different kind of structures that we are working here.
Okay. Following up with what Cassiano was presenting, we proposed a workflow, and in theory, everything works fine and everything is already rounded up. But when we are trying to implement this workflow, we have to find the right tools for what we want to implement. Getting a overall look, we have this workflow. I was talking about Excel here, where we get our first thoughts and the first interactions with our stakeholders. Then we get things more written in a better way, and we move on to Trace Cloud. And on Trace Cloud, we get all the logic, all the correlations, top level, low level requirements. Then when we have this structure and we are satisfied with it, we use RecIF as a converter for us to inputting our requirements into Capella. In Capella, there's the whole body of our operation. We have from the functional analysis, from the diagrams of what our experiments will be, until the full conceptual design. And in here, I've put some of the add-ons that we mostly use. We are mostly trying to implement to guarantee that we are getting the conceptual design right. We are dealing with the right models. We are doing trade-offs. We are using ANSYS Model Center, where we are able to get together models in Python, ANSYS, MATLAB, and another sources together, running in synchrony, and to compose a whole model. After this, some iterations happen, and when we are happy with our design, we can generate documentation from ANSYS Model Center, or the best way through Capella, the whole design in the complete form. Getting a more detailed view of each software, we start with Excel. And why do we start with Excel? Because we are already used to it. A lot of people do use Excel to do brainstormings, do different alignments, quick verifications between groups. And even in some projects here, we use it for quick checks and reviewing projects, but we never got to use it in a structured methodology. And that's what we are proposing now. We are trying to implement a way of documentation the birthing, let me say, of the requirements with its rationales, the type of it, if the quality of the requirement, because at first you get like a loose phrase, you have a loose need, and when you start working with the requirement, you get to write it in a certain way that it's more objective and gets more information to everyone around it. After getting everything in the first look that everyone can start to understand it, we move the requirements onto Trace Cloud. Trace Cloud is a browser-based tool that we can work in collaboration and to store our requirements. In Trace Cloud, we get dependency view, we get quick generation of report, version control, permissions control, which is very important for us because we work with, as Cassiano said and as Moreno said, with a lot of different groups at the same time, looking onto the same things, but at different point of views. And on Trace Cloud, we get to see the overall quickly. We have got to see the overall status of our requirements. They get sorted, identified, and classified by its origin. So this, for example, is a stakeholder requirement. And also you have a quick view of who created this requirement. If you have in doubt about which number, which phrase, you have the source of the information, so you can go back and ask what's happening. And also in Trace Cloud, we get to sort our requirements from low level to top level. In our case, mostly we get in upper levels, we get the experiment point of view, or what we want to give the science. And on the bottom level, we get the requisites for the components. And after we sort this out, we are ready to export everything into RecIF. Actually, right now we just use RecIF as a conversion tool because it's the format that Capella works better by what we've seen until now. And this brings us to Capella. Capella generates a lot of the information that we use. As Cassiano said, while in that framework, while we get the first contact with the stakeholders, we got to two different approaches. We get the requirements writing on, and we get the operational capabilities. We want our stakeholders to see and to share with us what will be in contact with what, the procedures and what happens during the experiment. And this we structure firstly on the operational capabilities diagram. Then we move on to the scenarios diagram, where we can get to the root of our procedures and be like step by step where information come from, where is it going on, so we can get a as clear as possible view for everyone about what we are going to deliver later. After getting on the scenarios, we are ready to start sorting functions out. So we have external functions, we get internal functions of our systems, we have functions that we have to deliver, but we don't know how. And this is the moment we start to map the relations between them, we start to form functional chains. And with the functional chains, we can start thinking about how we are going to deliver what we are being asked for. And in this case, we can start creating. Even in Capella, we can start creating. We can start proposing what motors we will use, what stages we will use, what's the good points, what's the down points. And with the experience, because here in the lab, as the guy said, we have a lot of experience, but sometimes we are not used to use strict methodologies. So it's in this moment that everyone gets to sit together and be proposing what they know, what they believe, and we sort things out on. After this first choosing of what we will use to deliver each function, it's time for us to model the solutions. And in this, it's time to get into our variables to see what information goes where, who is going to deal with information in which order. And in this moment, we get a lot of different pieces of work from a lot of different groups. We can have one beamline requirement written on Excel. We can have undulator models on Python, on DCM models and ANSYS, and we needed a way to bring this federation scheme together. And for us, besides being triggered by Capella, for us we needed to add another tool that was ANSYS Model Center. With this communication, we have different models proposed on Capella, but actually the testing, the comparing of solutions, the trade-off is done on Model Center. This brings us to ANSYS Model Center. In a quick view, from Capella, we get the creativity outputs. We have a huge list of what we can use, what we don't want to use, but we may be obliged to use. and we move everything onto Model Center. There we sort the models. We have a comparative study of them. We can do trade-offs, optimizations, optimal designs, and when we are happy with what we select, we can get all those parameters, organize them, and through an add-on, get the definitive project parameters back into Capella. Actually, we do this Capella integration following to the letter what's specified on this Obeo webinar. So we just thought about why not give it a highlight, because we didn't need to change anything. It was there and it was clear, and it's working for us. Last but not least, we don't use any more softwares, as these weren't enough. But as conclusions, where we are using a lot of things because we are tailoring a system for our team that's already used to work in the way it's used to work. So we cannot just be like, hey, stop everything. We will work on this strict framework from Cozy or as Arcadia right now. So we are getting the most value as we can from finding the right tool for each spot that we find a need, and getting everything together. And then in this, Capella is crucial because it has a lot of interaction possibilities. For almost everything that we are like, whoa, now we need to use this, we do a little research and like, oh, okay, we can integrate this with Capella. And together with all the functionalities, it's just the right tool for a job right now. Thank you. And any questions?
Right. Thank you very much, the three of you and Débora, for this excellent presentation. So let's see what questions we have. Okay, assuming that you are intensively networked with other synchrotron labs worldwide besides CERN, what is their experience with Capella in conjunction with deploying standard workflows like the INCOSY V model and advancing accelerator systems engineering?
Perhaps I can answer that. We are currently not networking with other synchrotrons for this topic now, since we are trying to show value within our own organization now. We saw the value of systems engineering even before model-based systems engineering. You saw the value of systems engineering for developing the beamlines that we have to develop, and this notion is also shared in other synchrotrons. But so far, all the developments are very incipient in the synchrotron community. We are trying to start something, show value, even though we are not applying by the book properly everything, to motivate the community to use it and to start building beamlines in a more efficient way, per se.
Yeah, thank you. And yeah, thank you, Gabriel. And on this delivering the value aspect, can you elaborate a little bit how you intend to demonstrate this value, or what type of maybe quantitative outcomes you would see or you would expect?
So what we expect to show value to our institution is that we have, as Gabriel said, 13 beamlines to build at the next 4 years. And we have a lot of different small components in the beamline that can be reused, and it's easy to be reused for each of them. So one of our first manners to show value with this is showing the easiest to reuse our models, or this to reuse our trade-offs and our documentations for this other beamlines. And also we plan to show value in it and how we can glue all this information together in a better way and have a better distribution of this information for all the companies. So we have a lot of people. It's hard, as mentioned in the other presentation. Also, it's hard to everyone understand the same thing for Word documents or Excel spreadsheets. So we try to do it in a more visualization way, in a more organized way, to more people to understand and more people work efficiently on the problems that we need to work, not everyone working problems that are parallel or problems that are not going to stick together at the end. So this is in our field is the two most values that we want to show to our company for now.
I think one thing that I might add to this answer is that, as was said on the CERN presentation, the physicists they don't have the MBSE mindset, not always, right? So to make the translations of language between engineering and physics, it's easier when you have a diagram and you start talking about the process instead of text, right? So it's really important to have this kind of not only the reusability, but also to diagrammatically see the processes that are taking place on, for instance, a biolab has many different processes that they might be conflicting with synchrotron, the synchrotron reality. So when we put everything inside the same module, the same model, we then are able to really grasp the let's say the aspects of the system that brings the performance. So one thing that we also kind of rushed to show something is within trade-off analysis. Of course, we are far away from showing something proper on that, but we wanted to we have, let's say, a federation of models here in Sirius that most often they work not together, not integrated, and then we have a lot of back and forth information from many areas, many disciplines from a beamline design, and then to really integrate that on the same model and show a trade-off analysis on that is something that we are starting to do now, but there's a long way to cover yet. So yeah.
Thank you, Cassiano and Gabriel, for your answers. Maybe a question more to Débora now. Do you link Capella with PLM ALM solutions, and which one, if so? I believe you are already connecting Capella with quite a lot of tools, but yeah, this is another question there.
Actually, right now we aren't linking Capella with these solutions, but we are thinking about some part of the project life management, because right now we are mostly worried about how we can get the project information, mostly the requisites along the operating phases of the Beamline, because right now we have the delivery, and when we deliver the system, it gets onto a whole different group. It passes completely to the hand of the scientific group, and sometimes the requirements get loose on this transition. And right now, on the point of view of life cycle management, this is our biggest, I believe, our biggest next step, to define a documentation or an easy way for them to access the project and have the parameters in a way they understand, not in a so engineering way of seeing parameters.
Right. And next question. Do you have to come back to update requirements due to physical constraints or other parts on Capella or MATLAB?
Up until now, we are updating the requirements onto Trace Cloud, and because I don't know, most because of the practicity, thinking like right now, because on there we we started chronologically implementing from the requirement, then we got into functions. So we got to Trace Cloud first, and there we have the tools to do that. So we just started doing the updates there, the versioning control of requirements there, and we got to link like the test result or the simulation result that got us to change. But I believe we can do this on Capella. It's just a situation from our application right now.
I'm not sure if this question also relates to when you do some optimization in MATLAB, for instance, you generate a new requirement and you go back to the requirement set. Is that related to that? If so, we haven't tested yet on our workflow, but I think it's possible. We might have a few examples to use, and probably we can show up in the next Capella days some advancements.
Okay, thank you very much. I think we went through the questions that we had for you today. Just another one, the last one that came in. What other tools, methods did you try for trade-off analysis apart from Model Center from ANSYS and MATLAB?
Not many. I would say for Camille we tried, but very, very, very slow. Actually, what happened with the Model Center is that we found out that we had a license in campus, and we started working. It was a kind of a lucky play, I don't know. So we started working with that due to the convenience that we already had this license here in campus, and it was very powerful to integrate many different language models, and also leaving Capella to do what it does best, that is architecture. So for instance, we saw Thales' presentation. We didn't get there yet, but it's one of our next steps. We want to do the functional analysis and selecting all the solutions in Capella, and then connecting it to ANSYS Model Center and perform the trade-off analysis from that, right? So this is within our plans, but has to be tested yet. I don't know if you guys want to add something. Yeah. Okay. So to the future.